Good morning, my YouTube viewers. It is Crystal here. I'm just here this morning because I was working on the Ames House Prices, and because I was working on the Ames House Price data set, I improved my score. And since I improved my score, I thought, well, I'd do a code review on this to show you what I did to actually improve my score. So you can see here's my Ames House Prices. My score was 0.14782, which was an improvement over my previous score, but obviously it wasn't my best score. My best score was like 0.12, I believe, but that was a really long time ago. So 0.14782 is an improvement over my previous score, and because of that, I wanted to do a code review on this. So the first thing we do is we talk about our problem statement, and this is the Ames House Prices. And what you have to do is you have to predict upon the house prices in Ames, Iowa. And I decided to employ a different tactic this time. I decided that I would try to improve my score by doing data cleaning. And when I was doing data cleaning, I just decided that since there were like 80 or 81 columns in the train and the test data sets, I decided that what I would do is, since there were so many columns, that I would just delete the columns that had null values. I thought that's the best way to go about this. Delete the columns that have null values. And so what I'm going to do is I'm going to show you how I did that. So the first thing I did was I imported my libraries of Pandas, NumPy, Matplotlib, and Seaborn. Pandas is a library that enables you to create data frames and manipulate them. NumPy is a library that enables you to carry out numerical calculations and also create NumPy arrays. Matplotlib enables you to graph your data points and plot them so you can visualize them. And Seaborn is more high level, and it still allows you to visualize your data, but it's built on the back of Matplotlib, but it's a more high level. So after I have imported the main libraries that I'm going to be using, what we did was we imported OS, which means operating system, and so we went into the operating system and we retrieved the files that we would need to make a prediction on these data sets. So we retrieved train, test, and sample submission. So, and then after we retrieved the files, what we did was we used Pandas to read the CSV file and convert it to a data frame. And you can see there's lots of null values here, and it had 81 columns. And then we took the test data set and converted that into a data frame, and you'll see there's lots of null values, and it had 80 columns as well. So that's a lot of columns to be predicting on, and some of these columns that have a very high correlation can be removed. And because there's so many columns, and it can also introduce noise into the system, and if it introduces noise into the system, that's going to affect the prediction. And then we check the submission. So this is the submission. This is what Kaggle wants to see when we submit our data prices. So the first thing we're going to do is we're going to analyze our sales price, and you can see that it is a bit skewed. And then now what we've done is we've made a box plot, so you can see how the higher the quality, the higher the price, and you can also see that there are some outliers in there. So now we're going to check for null values on train, so you can see that there's plenty of null values on train. So I wanted to see which columns had null values. So this is just testing to see which columns have null values. And then I dropped on train and test the columns that had null values. So now you can see train, it's only got 62 columns. And test only has 61 columns. And the reason why that is because the train has the label, and I haven't removed the label yet. So now what we're going to do is we're going to locate and delete outliers from the train file. So you can see that we've deleted the 8 outliers. We had 38 outliers. So what we're going to do is we're going to drop all the rows from the train file that have outliers. So that means we're going to be deleting 38 rows. So now we're going to analyze the sales price again. You can see that the sales price looks much better than it did previously because we got rid of 38 outliers. So now what we're going to do is we're going to make a copy of the train file, and then we're going to create a copy, which is a file where you append the test file to the train file, and we've dropped the sales price. So you can see now we've only got 61 columns on the combi. Let's see what we've got here. And previously there were 62 columns. So that just is telling us that we deleted the label. So now what we're going to do is we're going to drop the ID because we don't need the ID because it's just redundant. And the reason why is because we have an index. Now we're going to check for null values in combi. So what we're going to do is we're going to see check for any null values that we didn't get when we were deleting from the train and the test files. So what we're going to do is we're going to drop off these files, all of these columns again, and we're going to check for null values. There's 0 null values. And what we're going to do now is we're going to ordinal encode all of the columns that are objects. And the reason why that is because whenever we are performing predictions, the model won't work on strings or objects, and as a result of that we have to convert them to numerical values. So we have converted all of the object columns to numerical values, and you can see we have 45 columns. So we started out with like 80 columns, and now we only have 45 columns. So we've taken out 35 columns. So we reduced the number of columns, and so when we reduce the number of columns, that means that we're going to be reducing the noise. So now what we're going to do is we're going to do a heat map, and everything that has a high correlation does not need to be included in the features. And so I found this code. This is our correlation for everything. So I found this code, and basically what we're going to do is we're going to remove all of the columns that have a high correlation. And the reason why is if columns have a very high correlation, then that makes them redundant, and so you can delete one of the columns. But what happened here is what we were doing was we were checking for columns that had a correlation of greater than 0.9, and in this instance we didn't have a correlation of greater than 0.9, but if I wanted to reduce the number of columns that I already have, I could have made this 0.8 or 0.7 or even 0.6 or even 0.5, and that would have reduced the columns. But I was just thinking that since I had reduced the columns enough already whenever I was deleting columns that had null values. I just decided I would leave it as I did. And then what we did was we normalized the data, and when you normalize the data, what you do is you take all of the data points and you convert them to a figure of between 0 and 1. And the reason why is because some models, not all, but some models work better if the data is normalized. So you can either do it of three ways. You can not do anything to the data. You can standardize the data, which means it takes the median point as a 0, and anything below the median point is negative, and anything above the median point is a positive. Or you can normalize it, which is what I've done. And so what you're supposed to do is you're supposed to check all three scenarios, and you're supposed to use the scenario that gives you the best the best outcome. But I just decided to normalize it. I have standardized it in the past, but when you standardize it, you get negative numbers, and for house prices, negative numbers are not going to work. So I just stuck with normalization. I defined my x and my y variables. So y equals train sale price, x equals comb 0 to the length of train, and x test equals comb the length of train to the very end. And then I used sklearn's train test split to split the data set up into training and testing. And so I did that, and I decided what we're doing is we're doing voting at the moment. So we started out with linear regression, and with linear regression we had 82 when we trained the model and fitted it, and then we had 85 when we predicted on it. We had a pretty high error, 21,299, and then we had the actual values against the predicted values. And then so we plotted it on the graph. And so when you see that it's plotted on the graph, it doesn't look too bad. And now what we're going to do is we're going to check KNN. KNN worked better. It had 100% when you trained and fitted the model. It had 82.29% when you predicted on the validation set. And on the metrics, the RMS was 23721. And then what we did is we compared our actual values to the predicted values, so you can see how that worked out. So KNN worked better than linear regression, and you can see that we plotted that on a graph, and again you can compare the actual values to the predicted values. Now what we're going to do is we're going to look at extra trees. Extra trees had 100%. It's a very good model. It had a 90% when we predicted on the model, and it had an RMS 17328, which is better than the previous two errors. And then so we're going to compare the predicted values against the actual values, and you can also see the graphical depiction of the predicted values against the true values, and you can see that looks a little bit better. So now what we're going to do is we're going to use the voting regressor, and on the voting regressor what we do is we take the three models that we previously looked at and you combine them, and the theory is that the voting regressor is going to take the best level of accuracy from the three. So we had a 98% on the voting regressor, we had 89% when we predicted on it, we had our error, it was 17,858, and then we compared our actual values against our predicted values. We plotted it on a graph. You can see that the graph looks a little bit better because when you're using an ensemble, which is what a voting regressor is, the theory is that if you're using that you're going to get a better score if you use an ensemble, and so that's what we were using, an ensemble. And then so now what we're doing is we're predicting on the test set, called that PREDS. So anything less than 0 equals 0. But the reason why I used normalization was to try to prevent anything less than 0. And then we prepared our file for submission. And this is our sales price. And so that's it. That's the code review for what I did for the Ames House Prices. And I got a 0.14782, which was better than I've had in a long time. You know, perhaps I could have done a little bit more work to improve it, but since my score has improved, I decided just to leave it as it is. So I hope you like this code review, and I would like to thank my subscribers for supporting my channel. If you like this video, please like, subscribe, and share, and I look forward to making more videos for you in the future.